All right, today we're tackling a question that seems simple on the surface, but wow, the answer is huge. Where do waves actually come from? And here's a hint. The journey doesn't start in some storm out at sea. It starts with a star, 93 million miles away. It's a story of physics on a planetary scale. So let's dive in.
You know, if you hang out at any surf break, you might overhear a conversation that sounds a little something like this. And to the average person, it sounds less like two people talking about a sport and more like, well, like a scientific briefing from mission control. These guys are talking about weather fronts, pressure systems, and digging into super specific data from buoys floating hundreds of miles offshore.
And that right there brings us to our big question. I mean, it's one thing to say, oh yeah, storms make waves. We all kind of know that. But it's a completely different thing to understand the entire chain of events that kicks that storm into gear in the first place. The real story? It begins much, much further away than you'd probably guess.
Okay, so think of this image as our roadmap for this whole explainer. We're going to follow a single little packet of energy on its incredible journey, all the way from the sun right to the shore. You can see the whole chain of command right here. Solar energy heats up the atmosphere. That creates wind. The wind transfers its energy to the ocean, and boom, you get waves breaking on the coast.
So this leads us to this really fascinating paradox. You've got surfers who, just out of a pure simple obsession with riding a moving piece of water for a few seconds, accidentally turn themselves into scientists. I mean, they become these self-taught meteorologists and oceanographers, and they never even set foot in a formal classroom.
Yeah, their whole world really revolves around asking and trying to answer some pretty complex questions. Like, why do some waves peel just perfectly while others are just a mess and close out? Or hey, why did that massive storm we all saw on the weather map end up producing like zero surf? This constant asking why, that's the very heart of scientific thinking, isn't it?
All right, so let's start our journey at the very, very beginning, the ultimate source. Every single thing we're about to talk about, every gust of wind, every storm system, every single wave, it's all powered by the sun. It's like this gigantic battery that drives absolutely everything on Earth.
And it all kicks off with one simple fact: uneven heating. See, because the Earth is a sphere, the equator gets this direct, super concentrated blast of solar energy. Think of it like a focused flashlight beam. But up at the poles, that exact same amount of energy gets spread out over a much, much larger area. This temperature imbalance is the one thing that puts our entire atmosphere into constant motion, because it's always trying to balance itself out. Okay, so for a second, let's just imagine a super simple Earth. No continents, no mountains, and, this is key, no rotation. On a planet like that, the air circulation would be incredibly simple, just a beautiful, straightforward loop. Hot air would rise at the equator, travel up towards the cold poles, sink back down, and then flow right back to the equator along the surface. A perfect, predictable convection cell in each hemisphere. But, of course, our Earth is not that simple. Right, our Earth isn't simple at all. It spins, and this rotation adds a crucial, kind of weird twist to the story. It's a seemingly magical effect called the Coriolis force, and believe me, it changes everything. And you can see the effect of that spin right here. Instead of those two simple, tidy circulation cells we imagined, the planet's rotation completely shatters them. It breaks them into 6 distinct spiraling wind bands. And what this does is create these permanent belts of low pressure up around the 60-degree latitudes, which are just perfect breeding grounds for storms. And it also creates these belts of high pressure around the 30-degree latitudes. So what is this mysterious force anyway? Well, it's called an apparent force, and that's because it's kind of an illusion. An air mass is actually trying its best to travel in a perfectly straight line. But because we're standing here, watching it from the surface of a spinning planet, it looks to us like it's curving away.
This helps show why that happens. Check out the diagram on the left. Imagine a chunk of air, an air parcel, moving south from London. Now, because the Earth spins way faster at the equator, the ground down at Madrid is actually moving east faster than our air parcel is. So the air just can't keep up. It gets left behind, and from our perspective, it looks like it's curving to the right. As you can see, it doesn't matter which way the air is moving in the northern hemisphere. It always gets deflected to the right.
And this right here is the result that you see on every single weather map. Air always wants to rush from high pressure to low pressure, right? But as it rushes into that low, the Coriolis force yanks it to the right, forcing it into that classic counterclockwise spin we call a cyclone. And the exact opposite happens with a high pressure system.
Okay,
So now we've got these massive, spinning weather patterns established. So let's zoom in a bit and see how those big patterns give birth to the specific storms that are the true engine rooms of wave generation. These are the mid-latitude low-pressure systems. So a storm is basically born at this massive battle line in the atmosphere called the polar front. This is literally where cold, dense polar air clashes with warm, light tropical air. And all it takes is one little disturbance along this front. The lighter, warm air gets shoved up and over the dense, cold air, which causes the pressure at the surface to drop. Air rushes in to fill that low-pressure spot. The Coriolis force gives that signature twist, and boom, a spinning storm is born. And this is what a fully grown, mature storm looks like on a weather chart. You see those lines? They're called isobars, and they just connect points that have the same atmospheric pressure. Now here's the key takeaway. When you see those lines packed really tightly together, it means there's a huge pressure difference over a short distance. And what does that mean? It means you've got very, very strong winds.
And here's that exact process in action. This is a real North Atlantic storm just exploding to life over 48 hours. You can see it starts as just a tiny little disturbance, but fast forward 24 hours and it's getting organized, it's deepening. By the 48-hour mark, it's an absolute monster. A tightly wound low-pressure system that's just unleashing this huge field of powerful winds, pumping massive waves straight towards Europe.
All right, so we've followed the energy all the way from the sun. We've seen how it gets caught up in the atmosphere and how it gets concentrated into the powerful winds of a storm. Now it's time for the final, crucial step, actually transferring that wind energy into the surface of the ocean. But before we get into how waves grow, let's do a real quick primer on their anatomy. The key terms you need to know are height. That's just the distance from the bottom of the trough to the top of the crest. And period, which is the time it takes for two crests in a row to pass a single point. And these two things, they're about to get a whole lot bigger.
So how in the world does a totally flat sea turn into a raging one? Well, the whole process is explained by something called the Miles-Phillips theory. And it basically describes this two-stage process that involves a really fascinating positive feedback loop. This graph right here, it shows the pretty dramatic life of a wave inside a storm. See, at first, the growth is pretty slow and steady, but then it hits this critical tipping point and just explodes into a phase of rapid exponential growth. Finally, the wave kind of gets too big for its own good, and its growth levels off at a maximum size, or what we call a saturation point, for that particular wind speed. So, how does this all happen?
Okay, let's break this down. It all starts really small. You've got random gusts of wind and little pressure changes that create these tiny ripples on a calm sea. That's that initial slow growth. But, and this is the key, as soon as those ripples have some shape, they start to catch the wind. This creates a little high-pressure zone on the side the wind is hitting and a little low-pressure zone on the other side. This pressure difference literally pushes the wave along, feeding it more and more energy. And the bigger the wave gets, the more efficiently it catches the wind, and the faster it grows. That's the exponential explosion right there. Finally, the wave just gets so steep that it becomes unstable, and the top just breaks off into whitecaps. This releases energy and basically puts a speed limit on how big the wave can get.
And just like that, our little packet of energy is almost home. We've seen it travel across the entire solar system, get tangled up in the Earth's massive atmospheric engine, and finally get transferred into the ocean. It has been one heck of an epic journey.
So if we look back at our roadmap one last time, we've now followed the entire chain. From the sun's radiation creating that atmospheric imbalance, to the Coriolis twist creating the storms, and finally, to the wind pushing that energy into the ocean, creating the very wave that you see breaking on the shore. It's an incredible connection, isn't it?
And yet, after all of that incredible science, we kind of end up right back where we started, with that surfer scientist who knows that even with all of our computer models and all our charts, a 100% perfect prediction, it's just not possible. And you know what? Maybe that's for the best. It's the uncertainty, that feeling of anticipation, that keeps the wonder alive. And it makes sure that when that perfect wave does finally show up, we appreciate it all the more.